Hello everyone, welcome to Abhijit Codes. So in this video, we're going to solve the problem path with minimum effort. So what the problem requires is we need to return the minimum effort required to travel from top left cell to bottom right cell, and a route's effort is the minimum absolute difference in heights between two consecutive cells of the route. So let's understand the question with this example. So they are saying that we need to start from the top left corner and we need to reach the bottom right corner. We need to find the minimum effort for each route. Suppose this is a route, okay, 1 to 2, 2 to 3, 3 to 2, and again 2 to 5. And at each point we will get the absolute difference. So here the absolute difference will be 1, here it will be 1, here also it will be 1, and here it will be 3. And the maximum of all these will be the effort for this path. So for this path, over here, the effort will be 3. And if you are taking another path, let's suppose this. So the absolute difference here will be 2, here it will be 2, here it will be 2, and here it will be 2. So we see the maximum is 2 in. So our answer for this path will be 2 only. So similarly, we need to traverse all the possible paths. Like we need to check this path, need to check this, we need to check this path, and we need to check every path. And at the end, we need to return the minimum of the effort from all the paths. So at first glance, you might think that this is a DP problem, but we cannot solve this problem using DP because here the directions are that we need to go in all the four directions. So suppose we are starting our DP from point 1. So point 1 requires the result of 2 and 3 to be already calculated. So 1 will call 2 to calculate its result. Now 2 will require the result of 3, 8 and 1. We see that 1 called 2 and 2 is again asking 1 for its answer. So there is a cyclic dependency and thus we cannot proceed this way. So is there a way to solve this problem? So let's change this question for a bit. So let's ask this question that suppose if we know the effort, that means the minimum absolute difference of the path. So if we know the effort, can we answer if there is a path possible, if a path is possible or not. So let's suppose we assume that the minimum effort is 2. Okay, now what we can do is we first include 1 in our path. Okay, now 1 will go to its neighbor and check if there is any neighbor with absolute difference less than or equal to 2. So it will check this. So here it is less than equal to 2, and it will also check 2. So 2 also is giving less than equal to 2. So first it will suppose it is going here. So now it requires to check with 3 also. So it requires to check with 3's neighbors also. For this is already visited. So 2 will visit 3 and 2 will visit 8. In 8 there is no possible path going. So it will cancel this path. It will try going this path again. So here the difference is 1. So we again move on. Here also distance is 1. So we again move on. But here the distance is 3. F distance is 3. So we return back and come here. Now we explore this path. So we'll go 1 to 3. Then 3 to 5 will check. This has already been checked that 3 to 8 is not getting answer. So we'll not proceed in this path. Okay, we don't proceed this. We move from 3 to 5 and here the difference is 2. So we again check from 5 to 3 and 3 to 5, and at each point we find the distance to be true. So when we reach the last point, we return true from here, and at the end we this will return true if the difference was less than or equal to the given point. So what this problem has now become, this is now become a binary search problem. Binary search problem. That means we need to check for all the possibilities, and in the constraints you can see we have given from 0 to 10 to the power 6. So this can, from any point from these, can be a valid answer. So if you look at first, you might think that this is very long. 10 to the power 6 is a very long time and it might take very long. But the beauty of binary search is it cuts the search area in half at every stage. So suppose we have 10 to the power 6 at the beginning. So after, so this is suppose 10 to the power 6. So this will first try out for mid. Okay. If this is possible, it will try for lesser. And if it's not possible, it will move in this area. So after the first operation only, this has become 10 to the power 3. Then again, this will become 10 to the power 3 by 2. Then again by 2 by 2. So this will take just log of 10 to the power 6 base 2. And if we calculate it, what is log of 10 to the power 6 to base 2? We see that this answer is just 19 point something 93. Okay, so at max we require 20 operations only. So see how efficient is this binary search. From 10 to the power 6 options, we can reach the correct option in just 20 steps. Okay, that's the beauty of binary search. And for each iteration, what we require is we can require only big of n cross n time complexity at max. So this can go here. Yeah, so all the elements, suppose it is n cross n matrix, then at max we will require big of n square. So our overall time complexity will become n square log n. Or you can say log 10 to the power 6 base 2. So this is a much more efficient than any other operations. And also if we observe, we can find another way to solve this problem, and that is using Dijkstra's algorithm. Okay, so in Dijkstra's algorithm we see that we suppose each points to be a node. Okay, and the edge weight will be the absolute difference between them. So here edge weight will be 1, here it will be 1, and here it will be 7, and so on between each and every step. So using Dijkstra algorithm we can further reduce this time complexity to e log n, e log v, where v is the number of vertices. So here I have solved the problem using binary search. So let's see how the code is implemented. First we do the write the code for normal binary search. So we are requiring the rows, number of columns. Then the binary search will start from 0 and go till the max of 10 to the power 6. And in binary search we also require mid. I'm assuming answer to be the maximum possible. So I'm initializing it with h. Now we will move while this low is less than equal to high. And at each step, I will calculate the mid. Then I will create a Boolean vector visited. What is needed is it will check at each step that what vertices are visited already in the matrix or what cells are visited in the matrix. And if it is possible, then we will mark it as our answer and we will reduce the search area. We will try with lesser values at now. And if this mid is not successful, that no paths are possible with this effort, we will increase our effort to the higher search area. That means we will make our low equal to mid plus 1. So if you know binary search, this portion of code will be quite simple to understand. Now let's see what is the how to implement the is possible method. So here we use simple dxdy to go to visit all the neighbors. Okay. Then we are requiring heights given in the problem. Then I and j integers to visit the cells. Then we require the visited vector and the f here. F is the value of mid, or you can say the effort required, which we need to check that if it answer is possible with this effort or not. So if we reach at the end, we return true as we already seen in the example. And at each cell, when we are visiting, we mark them as true or visited. And now it's time to go to all their neighbors. Okay, so we go to all their neighbors and calculate their indexes. And if it is a possible index, we continue, else we skip. So if it's not a valid index, if either new I is less than 0, new j is less than 0, new I is greater than or equal to highest or size between row and column size, or this was already previously visited. This should not be here. Okay. Or this was previously visited, we skip this. Otherwise, this is a new cell we are visiting. So what we'll do, we will get the current absolute difference between this point and the new point. And if this is less than the value we are trying to check, then we will find the answer of this new point. Then what was your answer? We'll ask here. So suppose here one which one checks the 2, that this absolute difference is 1, which is less than equal to 2, and one also requires the result of 2 to be true, because if there is a path from 2 and I've already checked this difference, then we can say that yes, there is a path with difference 1, but we know that at the end this will result false from here. And then it will check with this 3 and it checks all the points, so this will return true, and finally this one will return true. Okay, so if both the conditions are satisfied, we need to return true, and if we have traversed all the neighbors and there was no path to be found, we will return false. So this is very simple. We need to write a each possible function and we need to do the simple binary search. Let's check if it is running. Okay, sample details are getting passed. Let's try to submit it. Okay, so yeah, thank you and see you in the next video.